So, welcome back. So, today we shall be trying to understand about or looking into more details about the advanced encryption standard, which we started to discuss in the last class, and we shall also touch upon the definition of side channel analysis, which is so important for hardware cryptography. So, the concepts that we shall be covering in today's class is that we shall be trying to look into the AES blocks. So, we shall be trying to go through the definitions of the various round operations in AES. And in this context, a very important algebra which we need to look into is what is called as GF2 algebra or Galois field 2 algebra, where we will try to look into how modular arithmetic is done in characteristic 2 fields. Okay. So, and finally, we will be trying to conclude with some challenges on cipher implementations. So, just to begin with, binary fields or binary finite fields essentially are finite fields which is denoted, for example, by the set S, and there are two operators which are defined. So, it is typically denoted by, say, a dot and a plus. So, a dot is often kind of realized as a multiplication and a plus is with additions, but essentially they can the definitions can be varied, and their definitions are just indicative of these two operations. So, therefore, right, you can basically take two elements in this field, and you can add, subtract and multiply, and you can also divide by any non-zero element. Okay. So, therefore, idea is that every element here which is non-zero should have a multiplicative inverse, and therefore, you should be able to multiply with the multiplicative inverse. Okay. And there is another very important rule which is called as distribution. So, the multiplication should distribute over addition. Okay. So, therefore, right, in binary finite fields, which is the the smallest form of the binary finite field, will typically have only two elements, which is 0 and 1, and that is also called as GF2 or Galois field 2. Okay. So, this is usually called as Galois field 2 or GF2. Now, there is an extension of this field which is called as GF2 power of m, which is essentially nothing but an m bit extension of GF2. Okay. So, therefore, here the 2 to the power of m is often the number of elements in S, and why it is very important to study GF2 based arithmetic or GF2 based algebra is because of the fact that various cryptographic algorithms, like for example AES, is reliant or constructed using binary finite fields. Okay. And partially it is done because of its efficiency. Okay. Like that if you, for example, have a GF2 arithmetic, then you basically can have only a single bit to indicate that data. It can either be 0 or it can be either be 1. A GF2 power of m element can be realized likewise by an m bit register. Okay. And therefore, you essentially have a very compact representation of an element in this finite field. Okay. So, and also, right, as we will study is that when you are, as we have also studied in our previous discussions, is that when you have got GF2 arithmetic, then many of the underlying arithmetic becomes efficient, becomes implementation. For example, if you remember, like when we are doing addition, then GF2 based additions can be done only by exclusive odds. Okay. Likewise, a squaring was very easy to implement. You just needed to interpose zeros in between, and you essentially had this basic squaring done, right. Of course, you had to do the final modular reduction, and also the final modular reduction when you are doing a modulo with an irreducible polynomial can also very efficiently be realized by only using exclusive odds. Okay. So, therefore, right, binary finite field based circuits are amenable to efficient implementations, and that is also one of the reasons why we have got very efficient architectures for the AES algorithm. So, therefore, right, if you really want to understand, again I will be resorting to the stick diagram which I cited in my last class. Okay. So, if I want to, for example, look into this, then there are certain weird things which happens in GF2 based arithmetic which we have to get used to. Okay. For example, suppose if I ask you, right, what is x plus x? Okay. So, the usual answer could be 2x, right, but in Galois field arithmetic, when you are doing x plus x, since the plus is nothing but exclusive OR, you essentially have 0. Okay. So, that is a very weird result which you get. Okay. So, likewise, right, there are certain things which will change when you are essentially doing your algebra in GF2 arithmetic. So, it is important to get used to this difference in algebra. For example, if I ask you to calculate x plus 1 square, okay, the usual answer is x square plus 2x plus 1, but when you are doing in GF2, then this 2x is 0. Okay. So, because 2 is 0, because you are doing modulo 2 arithmetic. Okay. So, therefore, the result will be x square plus 1. Okay, so therefore x plus 1 whole square is nothing but x square plus 1. Okay, likewise x plus 1 whole to the power of 4 will be only x to the power of 4 plus 1. Okay, so therefore, right, I mean the things will change slightly. Okay, therefore in the old ways, when we are, for example, having, when we are doing our computations, like then essentially what happens is that suppose you are doing say multiplication of two polynomials, or if you are adding two polynomials, right, then typically the things keep on increasing. Okay, but when you are essentially operating on finite fields, as the name suggests, it's finite, you have to do something which is called as a modular operation, right, so that essentially the field essentially has got finite number of elements. Okay, so therefore, right, usually as we have also discussed probably previously, is that usually these elements of the field or the finite field are represented as polynomials. Okay, so these polynomials are in X, and the coefficients of the polynomial are taken in the base field. That means, like, if I take a field of gf2 to the power of m, then an element in gf2 to the power of m can be represented by an m-bit register, or equivalently in terms of polynomial, it can be represented by a polynomial of degree m minus 1. Okay, so therefore it can increase from the degree can be from a constant term to m minus 1, and the coefficients of the polynomial are elements of gf2. That means they can be either 0 or they can be either 1. So when you want to operate on two such polynomials, and suppose you want to multiply two such polynomials, there is always a chance that the degree will exceed m minus 1, right. So if you want to bring it back to the field, therefore you need to do a modulo operation, and the modulo operation is done usually by applying or taking an irreducible polynomial which has got degree of m. Okay, and therefore once you do a reduction, that means you divide it and take the remainder, that means you take the resultant polynomial, divide by this irreducible polynomial which has got degree of m, then that would imply that the remainder has always degree which is less than m. Okay, that means the degree has the degree of the remainder is always maximum m minus 1. Okay, and therefore the remainder belongs to the field. Okay, so if you understand this, right, essentially you have basically understood the crux of GF2 arithmetic or finite field in general. So what essentially, for example, like when you are, so there are small differences, right, as I said, which we have to get used to. For example, right, if in the old way, right, when you are doing a computation, suppose you are doing a computation like in the old way, the coefficients could be as big as possible. Suppose when you are doing some arithmetic, you have got a coefficient which is say 123x squared plus 45x squared plus 678x plus 9x plus 10. So therefore you can see that in the old way, right, or in the usual algebra, we essentially often see huge or large number of coefficients. Okay, but in the new way, that means when you are doing these computations here, you have to reduce these coefficients. Okay, so you have to reduce this coefficient gf2. That means if you, for example, do it or reduce it here or apply it here, then 168 will be 0 because that's an even number. Okay, 687 will be odd, so it is 1. Likewise 10 will be 0. Okay, so therefore you will be left with only x. Okay, so therefore the in this algebra you will always have terms like x square plus 1 or x square XOR 1 also, alternatively as it is written, or we will have x square and so on. Okay, so for example here if I want to do say x square, so here as it is shown here, right, I mean you can see that I have got 123x squared. So the 123x squared is being written as x squared, that is 1 into x squared. Likewise 45x squared is nothing but 1 into x squared. 678x is like 678x, as you can understand, this is an even number, so therefore this should go away. Okay, and 9x plus 10 will be again x plus 1. Okay, because this is essentially your odd number. Okay, so likewise you can do this simplification, and finally you will be left with small coefficients. Okay, so finally here you have got only say like small coefficients, then the coefficients belong to either 0 or 1. Okay. So one important observation is also that in the new way or in the new definition, addition is same as subtraction. So therefore if you are doing say x XOR x, that is same as doing x minus x, and that is 0. So therefore addition and subtraction are same in both the cases, they are equivalent. Okay. So therefore right here this arithmetic is often understood by a clock arithmetic. So it's basically modular arithmetic. For example, there is 4 o'clock, if I add 10 hours, then we say it is 2 o'clock. Okay, because we are doing implicitly a modulo 12 operation. Okay, so likewise, right, when you are this is essentially called as modular addition, and like typically we also call that as developing a special group which is called as a finite field. Okay, So therefore, right, so we can probably take this example to understand the advantage of such kind of modular operations. Suppose I take a polynomial x to the power of 7 plus x to the power of 5 plus x cube plus x. Note that this polynomial is in gf to the power of 8, because as I said that when you consider gf to the power of 8, then that would imply a polynomial which has got a degree of maximum 7, okay, and therefore this belongs to gf to the power of 8. Let me take another polynomial in gf to the power of 8, say x to the power of 6 plus x to the power of 4 plus x squared plus 1, and then I multiply them. If I multiply them, of course I will get terms which has got degree, say 7 plus 6, that is x power of 13, okay. Now you can see that this final result, right, is quite big. So for example, I have got x to the power of 13 plus 2x to the power of 11 plus 3x to the power of 9 and so on till plus x, okay. So therefore, when you are doing modular arithmetic, we would like to reduce it and bring it back to the field, okay, and therefore you need a polynomial which is called as an irreducible polynomial, okay. And the other thing which you also need to ensure is that these coefficients are in GF2, okay. So therefore, what we do is that we try to, take a polynomial. For example, a usual polynomial here would be, say, x to the power of 8 plus x to the power of 4 plus x to the power of 3 plus x plus 1, and then we want to ensure that the result is brought back to the field, okay. So again, to understand how we do this modular operation, let us take a very simple operation, okay. Let me take a bx, where bx is nothing but b7 x to the power of 7 plus b6 x to the power of 6 plus b5 x to the power of 5 plus b4 x to the power of 4 plus b3 x to the power of 3 plus b2 x squared plus b1 x plus b0, and then I multiply it with x. Note that if b7 is 1, then I get b7 x to the power of 8. Now the moment I get b7 x to the power of 8, I know that this element does not belong to the field, because the degree exceeds 7. So therefore, we have to basically make it smaller and we have to bring it back to the field, okay. And therefore, the usual way of doing that is by taking this polynomial and dividing by this polynomial, which is mx, x to the power of 8 plus x to the power of 4 plus x to the power of 3 plus x plus 1. Now this is an irreducible polynomial, okay. So what I do is that this is something like I do a modular arithmetic, like what we do in modular arithmetic. Here also, when we work with polynomials, we do exactly the same. So I take this polynomial, divide this by this polynomial, and I get the remainder. The final remainder is being shown here, and this remainder essentially belongs to the field, okay. So therefore, the final why it belongs to the field, because you can see that the maximum degree here is 7, okay. Therefore, this belongs to the field. So therefore, right, so therefore, like what you can do is that rather, rather working with polynomials, when you are trying to think about implementations, a better way is to realize that is in the form of registers. So what you can probably do is that, suppose I have got a polynomial like x to the power of 4 plus x to the power of 3 plus x plus 1, I can represent them by a by a register which has got 8 elements, okay. For example, here the elements would be 0 here, because this degree is 0 here, it is not there in this particular element. Likewise, x to the power of 6 will have a coefficient of 0, x to the power of 5 will have a coefficient of 0, x to the power of 4 will have a coefficient of 1, okay. Likewise, you will have x cube plus 0x squared plus 1x plus 1, okay. So therefore, this number is nothing but 0001, and that therefore in hexadecimal I can denote it as 1, and here I have got 1011 in hexadecimal, this is b, okay. So therefore, right, I can actually represent this by a single byte, 1 byte, which is denoted by this hexadecimal notation, which is 1b. So therefore, 1b also stands for this polynomial. So therefore, what we will probably try to write now is that we will try to work with, say, these numbers 1b, and when we are operating with 1b, whether we are multiplying, adding, right, we will basically implicitly we will be doing finite field operations, okay. But this gives a very nice compact representation of a GF2 power of 8 element, okay. So therefore, right, when we are trying to say, when we are trying to construct a field, a very important property of being a field is that every non-zero element should have a multiplicative inverse. That means, suppose if I give you this 1b, which is essentially standing for this polynomial, there should be an element with which if I multiply, I get back the multiplicative unity, which is 1, okay, which is nothing but the polynomial with one single constant, that is 1, okay. So therefore, right, I should be able to find out this corresponding element, which if I multiply, I should get back a 1, okay. There are different ways, as we have studied in the last class, of computing multiplicative inverses. You can apply Euclidean algorithm or any other algorithm for that matter. But we should also understand that when you are like realizing it for a small field like for AES, which is realized on GF2 power of 8 arithmetic, you don't need to apply the a general algorithm for computing the inverse. Okay. So one very naive way would be, let me store all the inverses, let me store all the multiplicative inverses for non-zero elements, and that would mean that I need only 255 storages, right, because I need storages for 255 elements and I can get the corresponding inverse in order one time, right. I can just get directly the inverse, and I can do that with a small amount of storage. So, therefore, right, I mean, let us try to understand how the substitution box or the S box of AES looks like. Okay. So, if you have understood how to or rather the idea of multiplicative inverse, then the representation of the S box becomes very easy. Okay. So, what you do here is by two steps. So, therefore, suppose that in the S box you essentially have an input A, okay, and if I apply G of A, then I get A inverse, which is the multiplicative inverse. And likewise, the next step which you do after computing GA is to apply an affine transformation. So, the affine transformation is done by taking the result of A inverse, which is denoted as A7 to A0. Note that this register stands for an element in GF2 to the power of 8, and then I apply a matrix, I pre-multiply with a matrix which is fixed, and then I add another matrix. Okay. So, therefore, I get like a corresponding result, and therefore, the final result is essentially the corresponding output of this affine transformation. Okay. So, for example, therefore, if I want to calculate, say, the S box of 58, so note that 58 stands for the hexadecimal notation of 5 followed by 8. Okay. So, it will be basically 0101, that stands for 5, and likewise your 8 will be 1000. Okay. So, 1000. So, therefore, if I take this, then first I will calculate the multiplicative inverse of this, which is essentially here 18. Okay, and you can calculate that if I multiply 58 with 18, okay, and then apply the modular as a modular polynomial, that modulo polynomial, which is essentially x to the power of 8 plus x to the power of 4 plus x to the power of 3 plus x plus 1, then I should get back 1. Okay, I should get back 1 here. And finally, right, I apply the affine transformation, which is shown by this matrix plus this vector, and then I get the result, which is 6A. So, that means 58 will get mapped into 6A. Okay. So, this mapping is predetermined in case of AES. That means this S box, either you can like pre-calculate this and store in the form of a table, and the size of the table, as you can easily understand, will be of dimension 256, because there are 2 to the power of 8 possible inputs that you can give to this S box. It operates on 1 byte of information. Mixed column is probably the more like complicated algorithm, complicated step, where you basically take like each of these columns. So, in AES, as I said that in AES 128, a state is represented as in this form. Okay. So, it is represented as a matrix. So, this matrix has got 16 bytes. Okay. So, you can either visualize them as 16 bytes, or you can visualize them to be made of 4 columns. Okay. And each column has got dimension of 32 bits or 4 bytes. So, in mixed columns, what you do is you take one of these columns and you transform them and get another output column. Okay. And how do you do this transformation? Is by taking this column and writing them as another matrix, say Ax, or another polynomial, say Ax, but Ax now has got elements, okay, such that like I can write Ax as A3 x to the power of 3 plus A2 x squared plus A1 x plus A0. Note that all these coefficients A0, A1, A2 and A3 now belongs to GF2 power of 8. And now what I do is that I multiply it with a fixed polynomial, which is a special polynomial, and then I take modulo x to the power of 4 plus 1. Okay. Note that x to the power of 4 plus 1 is not an irreducible polynomial in this field. Okay. And therefore, all elements will not have multiplicative inverse. But at the same time, if I want to apply, to get the decryption, I need to ensure that this special polynomial has a multiplicative inverse. Okay. So, therefore, it indeed happens, right, that for this particular polynomial or reducible polynomial, this polynomial has a multiplicative inverse. Okay. And therefore, right, we can apply a decryption process. So, in the encryption step, what we do is that we take this polynomial, we multiply it with this special polynomial, and then apply modulo x to the power of 4 plus 1 to get another result, which essentially also will therefore have can be represented as shown here x cube with like degrees like x cube, x squared, x and constant term, where the coefficients are as shown here 2a3 plus a2 plus a1 plus 3a0, For x square it will be 3a3 plus 2a2 plus a1 plus a0. Likewise for x it will be a3 plus 3a2 plus 2a1 plus a0. Note that these operations like 2a3, 3a0, they are done in GF2 power of 8. They are not integer multiplications. Okay, so therefore when you are doing 2 into a3, that means you are multiplying 2, which stands for the polynomial x, with a3, which is the element in GF2 power of 8. That means you can represent a3 as to be made of like a register which has got register of dimension 8, and each of them are 0, 1 values, or you can imagine them to be as a polynomial which has got a degree of maximum 7. Okay, and therefore when you multiply it with x, there is always a term of overflow. The moment there is an overflow, again you apply the irreducible polynomial, as I said in the previous slide, and you bring the result back to GF2 power of 8. Okay, and finally you essentially try to compose them, and you essentially get this coefficient. Okay. Alternatively, there is a very simple representation of this transformation, which is done through this mixed column matrix. So here you take this column, which is denoted as a3, a2, a1, a0, and imagine that you are basically pre-multiplying with this matrix. Okay. So this matrix essentially has got elements 2, 1, 1, 3, and then there is a cyclic shift of these elements. So you can see that I get 3, 2, 1, 1, 1, 3, 2, 1, 1, 1, 3, 2. Again note that all these elements belong to GF2 power of 8. So therefore the multiplication is done in Galois field 2 to the power of 8. Okay. And finally you get the result, which is shown as B3, B2, B1, B0, which is nothing but the transformed column. Okay. So you apply this column by column, and you essentially transform the entire state matrix, and you get the result after the mixed column operation. So therefore, let us take let us summarize these steps what we have seen. The first step is the add round key. So in the add round key, you take a state of the AES 128. We have got a key. Again, this key is nothing but a 16 byte data, which is again represented by this tabular representation, where every element is a byte. Okay, and then you do an exclusive OR. This is your key mixing step, and you get the final result. Okay, here this plus stands for exclusive OR, where you are doing a bitwise exclusive OR. Then there is an important step which is called as shift rows. In shift rows, you take this particular state matrix, and you see that in the first row I do not do any shift. Okay, so therefore if the first row is AEIM, I essentially have got AEIM in the output of this transformation as well. But if you see the next row, then for example BFJN, then you will see that I do a cyclic left rotation. Okay, so therefore B comes here, F comes here, J comes here, and N comes here. So I do a cyclic left rotation by 8 bits. Okay, that means by 1 byte. For the third row, I do a cyclic left rotation, but now I do it by 2 bytes. So therefore, like K will come here and so on. So I will get KOCG in this case. The final row essentially is done again a left rotation, but now it is by 3 bytes. Okay, you can alternatively think of this as a right rotation by 1 byte as well. Okay, so therefore DHLP will therefore come here as D will come here, H will come here, L will come here, and P will come here. Okay. So finally, you can also realize that if you want to realize that by a hardware, then you don't need to waste any resource, because you can do this entire mapping by just wirings. Okay, you don't need any explicit step for doing this computation. You can just do a wiring, and therefore without any resource you can achieve this transformation. Okay, inverse shift row can be again done similar way. This is just the opposite operation, and which you can again do by a wiring operation. Finally, you have got the mixed columns. As I said, that for the mixed columns, you basically have to realize this column transformation, where you take this column, apply this matrix. So this matrix is what I just now described, where you have got elements in GF2 to the power of 8, and you have to multiply or pre-multiply this matrix with this column to get the final result, shown here as capital E, capital F, capital G, and capital H. Okay. So likewise, as I said, that the matrix is chosen in a way so that it has got an inverse, and therefore this is the corresponding inverse, which you can see is slightly more complicated than the forward transformation. And then once you have got this right, you essentially can again pre-multiply with the result, and you should get back the original data. So here, as you can see, that I have taken this input and again got back this, so this should give me back the original data. Okay, the hardware implementation can be done in a similar way as the mixed columns. Okay, and we will be studying this in the next class of more specific details about these implementations. Finally, as I said, the byte substitution or the S box, which provides confusion, is a nonlinear transformation. So here you do an affine you do an X inverse computation in GF2 power of 8, followed by an affine transformation. For 0 as an input, then you assume that 0 is the corresponding inverse of it. As the inverse is not defined, we make a special case for that and say that okay, the inverse of 0 is 0, and then I do a final affine transformation on that. And finally, this is the affine matrix as shown here. These matrices or vectors are predefined and pre-designed, and therefore I can define the transformation for AES S box or byte substitution. So finally, what I do is that, for example, if I want, I can store this in the form of a table. So what I can, for example, suppose my input is 4 2. So what I do is that in that table I have got like a tabular representation where the rows are indexed by numbers from 0 to f, and the columns are also indexed from 0 to f. So therefore, if 4 2 is my input, then I see the corresponding row here, and I see the corresponding column here, and therefore 2c is my result. Okay, so therefore I can also realize this by a nice tabular representation. Although this may not be the best way of implementing it, but at least we understand how we can like possibly realize such kind of mapping. Okay, so we will be studying in the next class about more details about how to realize this S box operation. So talking about, like, finally our goal is to develop a hardware design, but one of the very important so basically in the classical sense, right, what we have discussed in the previous discussion or lecture also, that you have got Alice and Bob, and you have got an attacker which is either Eve or Mallory or some eavesdropper who is trying to observe this communication channel. So therefore, what we essentially assumed in the classical sense was that only Alice knows Ka, only Bob knows Kb, okay, and Mallory has got access to the encryption algorithm, decryption algorithm and the communication channel, but does not know the decryption key. Okay, so this is the classical scenario. But in real life, when you have either a hardware design, or if you have an embedded design, or you have any implementation for that matter, then the attacker can try to look into several other information sources, and these are what are called as side channels. So in the side channels in the real world essentially stand for those unintentional or even unintentional information leakages which can happen in the real world and can compromise your secrecy. Okay, can compromise the information about the secret key. So therefore, there can be several side channel sources. Okay, so the cryptographic algorithms, like the threat models and the security goal is also important. Okay, the protocol is important, the software is important, whether you are doing a hardware design is important. Okay, and finally your deployment and usage is also very crucial. Okay, and of course you have the human users. Okay, and it is almost impossible to design a totally secure system with humans in it. Okay, but rather, right, what we will be trying to look into is not those aspects, but more as we have traditionally been handling only cryptographic algorithms. In this course, we shall be trying to look into more of the hardware and the software leakages. For example, in software you can have key dependent variations, computation times and so on, which we will try to see how we can exploit and also suitably safeguard against. And in hardware, of course, you have got several side channel sources like power consumptions, EM radiations, test methodologies, behavior under faults, which all can lead to efficient mechanisms of attacks. Okay, and therefore, when you want to really make secure hardware, you need to take care of these threat scenarios and properly address them. Okay. So therefore, right, the fundamental claim here is that strong cryptographic algorithms are important, but they are just the beginning. So it may, in this scenario, for example, take a smart card and take it to a card accepting device, have a nice encryption algorithm. So when you are just restricted to only input and output exchanges, then this may be safe. Okay, but in the real world, right, there may be, for example, power supplies. Okay, and that power supply can trivially leak the key. Okay, and therefore, right, for example, like if you have studied, for example, the Rsa algorithm, right, the Rsa algorithm does a square and multiply operation. Okay, and therefore what may happen is that from the power consumptions here, depending upon the glitches or just seeing the glitches of the power rail, you can probably infer that the secret key was 0. Okay, where and if the glitch is more, or if this is more, then you see that probably it is doing an additional step, and the additional step is probably a multiplication. Okay, and therefore it will give you the secret key in an order n amount of time. Okay, in a linear amount of time. So therefore, you are not really challenging the mathematics behind RSA, but you are just having a very easy way of getting the key, but your target is mainly the implementation. Okay, and therefore it also ensures that our implementation should not be efficient as well only, but at the same time also should try to restrict against these kind of attack vectors. Okay. So therefore, what are side channels? Right, these are typically covert channels which leak information which the designers of the cryptography algorithm did not consider. And often you will find that they take place because of optimizations. Okay, these optimizations either are done intentionally by us or unintentionally by maybe the compiler or by other artifacts, which essentially tries to optimize our designs and try to only concentrate on performance. Okay. For example, when you are trying to realize the square and an exponential algorithm which you want, for example, for RSA, the reason why you have square and multiply is because of efficiency, right? You have an if else structure so that you ensure that you get the result in a very efficient manner, and that is precisely the thing which you target in side channels. Okay. So therefore, the optimizations are often like what are targeted by a side channel adversary. So therefore, our optimization should also take care of such threats if you really want an end-to-end security. So therefore, there are a lot of challenges for a cryptographic designer. It has to, of course, take care of overhead. As I said, for cryptography, the algorithms are very computationally intensive. If you are talking about symmetric key algorithms, there are a large number of rounds. It uses nonlinear Boolean functions which needs to be suitably implemented. Asymmetric algorithms often operate on large numbers. It performs complex mathematical operations, so we need to make them efficient. So therefore, there are definitely the usual challenges of performance, size and power, but to make it more interesting, you also have to tackle information leakages through covert channels like side channels. Okay. And therefore, if you really want a secured implementation, you need to have an end-to-end spectrum of things. Okay. So again, I would like to stop here, and again, this is my usual reference for this part of the lecture. And what we have essentially discussed today is that we have discussed about AES. We have looked into the AES steps like add round key, byte substitution, shift rows, mixed columns, and also essentially discussed that these sub operations are defined in the finite field GF2. We also discussed about what are side channels, and we kind of reflected that if you really want to have an end-to-end cryptographic hardware, then you also need to look into not only performance but also these threats. Okay. And that essentially we will see in the following classes of how to slowly address on. We will try to understand not only the attacks but also how to counter them in the future classes. Okay. So with this, I would like to thank you for your time.